Hi everyone. Today what we're going to do is we're going to take some of the work that we did in our last video, working through on rotation angles and the introduction of rotation angles, and we're going to start to go through and solve for trig ratios. So what we want to do is we want to work our way through then coming up with the exact value of a trig ratio. So if you'll take a look at problem 1, you'll notice that you could come up with approximate values for each one of these ratios, potentially, by using your calculator and pushing some buttons. Today, what we want to walk through is a way to go through and come up with the exact value of each trig ratio with no technology. So let's take a look at the first one. When you see the cos of 60, I would expect that everybody should be sitting at this point and saying that they recognize that 60 degrees is a special angle and they could draw a triangle that includes that special angle. And so if you were to produce a right triangle, you would say 60 degrees is a large special angle, and if it's the large special angle, then it has the large opposite side. And therefore, you know that the three sides of your 60-degree special triangle are root 3, 1, and 2. And you would have the means then, using that triangle, to come up with what your ratio was, and cos is saying adjacent over hypotenuse, and so it would have a value of 1/2. As we take a look at that, I'd just like you to notice, all we would ever have to see is the blue. So if you are very comfortable with your special angles, and you're very good with that, and you know them, you never have to show us the picture in red. However, until it is automatic for you, what I would say is I would recommend drawing that triangle every time. Now, let's take a look at B, because problem B becomes a little more difficult. And what I want to do is I actually want to backtrack and take a look at A, but in a slightly different way. That we could come to a very universal way of coming up with the exact value of each trig ratio if we use rotation angles. So if I was to tackle A all over again, I could go through and produce a quick set of axes. Why am I doing this? Because when I take a look at problem B, it's very difficult to draw a right triangle that has an angle of 135 degrees in it. In fact, it's impossible. So I need another method to deal with that. So if I stick with my green, then I know that a rotation angle of 60 degrees would put my terminal arm somewhere here. And now what I need is I need my triangle. And so what I can always do is pick a point on my terminal arm, and I can drop in my height with my x-axis. Notice that that 60-degree angle is my related acute angle, and it is contained inside that triangle. Well, now all I need to do is label the sides of that triangle. A 60-degree angle is my big special angle, so it has a big opposite side. Fill in the rest, and we have enough on that diagram to determine that the cos is 1/2. That green solution then becomes a universal way for us to be able to work our way through rotation angles. So let's jump into B, and let's see if we can work the same way. So first thing I'm going to do is jot down a quick set of axes. I'm going to keep that in green. Well, now my first job is to figure out where does the terminal arm lie for an angle of 135 degrees. So let's use this as a quick check. Pause the video, see if you can get your terminal arm to lie in the correct position. Okay, we're back. And so we should have our terminal arm lying something like that. We know that this angle produced, my principal angle, is 135 degrees. Okay, now we need to do everything that we did before. So let's pick a point on our terminal arm, and let's drop in a height. Now, what I'd like everyone to do is to label the related acute angle inside that triangle. Pause the video, go. Okay, we're back. And so, if I was to then take 135 degrees to rotate, would mean that I was 45 degrees short of 180. All the way around to my negative x-axis would be 180 degrees, so I am 45 degrees as a related acute angle. Now what I'd like everyone to do is to label the three sides of that 45-degree special triangle. Pause the video now. Okay, and we should be back. Now, what I would expect to see on a lot of people, and I think this is great, is if we were to look at that 45 degree and know, I know that the three sides of a 45-degree triangle are 1, 1, and root 2. If we have that, outstanding. However, there's a mistake that we have on there. And perhaps we can remember back from our previous lesson, but when I look at this opposite side of 1, I'm going up 1 unit from my origin. I went up 1, so I have a positive 1. When I take a look at my adjacent side, here's where I have an issue. We went to the left 1 unit, and therefore that 1 should really be a negative 1. Now we have the three sides of that triangle labeled correctly, and so we can calculate tan. Tan is going to tell us to take opposite over adjacent, and we can simplify that down to negative 1. What I'd like everybody to do, since they trust their calculator more than they trust us, go ahead and push some buttons on your calculator and get a little confirmation. Good. So what we have in our solution for B then is a functional way to work through any rotation angle to come up with an exact value for our ratio. So let's take a look at the two problems that you have on the screen right now. And I think that just based off of our solution to B, we may have a bunch of people who feel very comfortable to work their way through C and D. So I'm going to ask everybody, pause the video and give C a shot. Okay, we're back. And so if I see C, problem C, then I know that I'm going to put down a quick set of axes, and I need to now rotate 240 degrees. Well, I know from standard position, if I rotate to my negative x-axis, that's 180 degrees. So for me to rotate 240, my terminal arm should be down here somewhere. And in fact, as soon as I know that my terminal arm is there, I probably came up with my related acute angle at the same time, 60 degrees. Okay, I need to create my right triangle so I can drop in a height. And now that I see that triangle with this 60-degree special angle contained, I can label my sides. My 60-degree angle is my largest possible angle, which means it has the largest opposite side. I can fill in the rest of the sides based on my special triangle. And now I caught myself, and I noticed that I have the actual side lengths in proportion, listed in blue, but I have not put anything with regards to direction. That 1 that I have went to the left, which means it should have been negative 1. And the root 3 that I have went down, so I should have had a negative root 3. Finally, that triangle is properly labeled, and the only thing to do now is to determine cos. Cos is adjacent over hypotenuse, and we now have the exact value. Again, you have your calculator to help you to go through and do any confirmation. Okay, for anybody who's a little nervous about C, let's pause the video and give D a shot. Okay, we're back. And so we take a look at 330 degrees, so I can jot down a quick set of axes. If I was to now rotate 330 degrees, I should be quite comfortable to have my terminal arm here. I know that all the way around is going to be 330 degrees, and so I know that my related acute angle is going to be 30 degrees. Now that I have that, I can drop in my height to construct my triangle. And now I need to label my side lengths. So 30 degrees is my smallest special angle, which means that that has my smallest opposite side. I can label in the other sides of that special triangle. And now I don't forget about direction. So the only adjustment I need to make now is to make that one a -1 because I went down. Now that I have all three sides labeled, I can finally calculate my sine ratio. Sine is opposite over hypotenuse, and there's my value of -1/2. So hopefully 2 quick determinations for us, not too bad. And so now what you'll see is you'll see 2 last problems that we're going to determine exact values for our trig ratio. So in question E, we need to figure out the tan of -225, and for question F, we need the sine of 675. I'd like everybody to pause the video to work their way through these 2 problems. And we're back. So on my E, I think the biggest issue for us on E should be, did we put our terminal arm in the correct spot? So for me to rotate negative, I need to begin on my positive x-axis and begin moving down. So for me to rotate that -225, there is at least -180. And so for me to then go and continue to 225, that might be my terminal arm. I should then be able to figure out that my related acute angle is 45 degrees. And remember, all related acute angles are always positive. And so then I can drop in my height, and now I need to label my triangle. And so if I have a 45-degree angle, then I know my sides are 1, 1, and √2. And now I just need to put on my directional symbols. So I went to the left 1, which means that on my adjacent side should be a -1. Now that I have my side lengths labeled, I can determine my tan. Tan is opposite over adjacent, and I get a value of -1. So we take a look at F. The only difference in F is I gave you a really big angle. So for us to be able to work our way through, I'm going to have a quick set of axes. And now I need to rotate 675 degrees. Well, clearly a full rotation is already going to go in there. So I need to do a little calculation of what 675 is, subtract a full rotation. And if I take 675 and I subtract 360, I get 315 degrees. So on my diagram, I am going to go around a full rotation and then another 315 degrees. That is going to put my terminal arm into quadrant 4. If I rotate 315 degrees, then I'm going to be 45 degrees short of getting back to the x-axis. Now that I have that related acute angle, I can drop in my height, and I can label my side lengths. And so my triangle then, 45 degrees, is a 1, 1, and √2. I have my directional symbol on to say I went down 1 unit. And for me to calculate my sine is then opposite over hypotenuse. And there we go. So 6 relatively quick problems for us to have the means to be able to find the exact value of any trig ratio. Good work. So we're going to change gears a little bit now, and I'm just going to give you a moment to read the problem on the screen. What we're going to do is we're going to go back and address something that we did in the previous lesson, but we're going to kind of nail down some specifics in it. Okay, what I want to do now is I want to just break down some of the key components in here. It says determine the value of each trig ratio. And so if it doesn't state approximate, then we need to know that that means that we need to come up with the exact value. So I need the exact value of a trig ratio. Or sorry, the exact trig ratio. Secondly, what we have is we have point P is on a terminal arm if theta is in standard position. And so since my angle is being created in standard position, I know that I'm beginning to rotate from my positive x-axis. And lastly, and a very important statement, I've been told that theta has to be greater than or equal to 0 and less than or equal to 360 degrees. What that restriction states right there is one positive rotation. So if we can get to the point where we start to read that restriction, not as theta is greater than or equal to 0 and less than, no, we can see that terminology, but instead translate it to the blue statement. One positive rotation, then I think that's going to give us some greater context. So you need to come up with the value of each trig ratio, when point P is on a terminal arm, if we rotate from standard position, and we're only doing one positive rotation. So let's take a look at point A, and I think problem A, I think everybody should be able to draw a diagram for A. So pause the video, create your picture. Okay, we're back. So I have my set of axes. I noticed that point P would put me at -2, -5, so I would be down here somewhere. That means that my terminal arm must pass through that point. I'm going to label that point. I'm just going to put it out here a little bit to give me some space. Okay. On my diagram then, this is theta. Rotating from standard position, one positive rotation. And now what I can do is I can go through and determine the value of each trig ratio. So to come up with the value of each trig ratio, I need a triangle, which means that I'm going to drop in my height. And when I drop in that height, I am now going to be able to label the sides of that triangle. Because I went to point -2, -5, that actually gives me the side lengths on that triangle, as if I were counting out squares to plot a point. I went to the left 2 units, and I went down 5 units. Now that I have those two values labeled on the triangle, I could start to work my way through coming up with each trig ratio. I've been asked to come up with the exact value of what sine theta, cos theta, and tan theta is. So right now, I can only come up with one of those ratios. We should see which ratio that is, because the only side lengths I have on that triangle are adjacent and opposite, which means the only thing I can come up with is my tan ratio. My tan is going to be opposite over adjacent, and I, of course, am going to simplify that to 5/2. Now, what I'm missing on that triangle is the hypotenuse. And so for me to be able to come up with my sine and my cos, I will require the hypotenuse. So I'm going to have to do a little bit of work. And for me to come up with that hypotenuse, maybe I call that C. Then I know that C squared has to equal one side squared plus the other side squared. So C squared has to give me this, and that means that the length of my hypotenuse is root 29. Remember that because a hypotenuse is on a diagonal, it does not have a directional component. So all hypotenuses are positive. And now that I have that, I can go through and I can determine my exact value. So the sine of it is opposite over hypotenuse, and the cos of theta is adjacent over hypotenuse. And there we go. Perfect. Now, I could ask you to come up with one other item on this diagram. It's not in the original question, but we could come up with the actual angle measurement of theta. I want you to notice and recall from our last lesson, if I was to use any one of my 3 trig ratios, I know which one I'm going to use. I'm going to use my tan ratio because I didn't really come up with that one. I didn't have to calculate the hypotenuse, so any risk for mistake is lessened. So for me to go through then, I need to come up with the related acute angle. I'm going to call that alpha. So alpha would then have to be the inverse tan of 5/2. And so if we take out our calculator and we do the inverse tan of 5/2, then we're going to get that alpha is approximately equal to 68 degrees. And therefore, you could come up with what your measurement was for theta. Because you know that theta is rotating 180 degrees to get to your negative x-axis. And now you just found that you have to go an additional 68 degrees to get to your terminal arm. So if I took my 180 and I added to that the 68, then I could come up with my 248 degree principal angle. So hopefully not too bad to walk through that one. We had a lot of information in that one problem. Now I want to walk through one more problem where we deal with a point on the terminal arm. So I'd like you to go through and address point P lying at 0, -8. So first thing we're going to do, we're going to create our diagram. So let's put on a quick set of axes. And I know that my terminal arm, if it lies on point P, which is at 0, -8, then it would lie here. And so if I were to draw my terminal arm would have to be going straight down. Now, I just want to kind of come and address one key item. Right now, we may be struggling to come up with the sine of theta. Because when we take a look at theta, there's my theta. And for me to come up with sine, I need to know opposite and hypotenuse. And I'm having a real tough time even seeing a triangle there. I may notice that my cos is the same thing and my tan is the same thing because I don't have a triangle. However, I would expect everyone right now to be able to tell me what was the angle measurement of theta. For us to get to the negative y-axis, we had to rotate 90, 180, and 270 degrees. So notice that when my terminal arm was lying on an axis, my angle measurement was easy to come up with, but my trig ratios I'm struggling with. So perhaps a conclusion we draw is maybe you don't have trig ratios when your terminal arm lies on an axis. I'd like everybody to go ahead and push buttons in their calculator right now. And instead of having just generically theta there, I'd like you to calculate the sine of 270, the cos of 270, and the tan of 270, and see what we can come up with. Okay, when you did calculate those values, you should have found that your sine of 270 was -1. You should have found that your cos of 270 was 0. And so just even in the calculation of those two, you would go, well, if I can calculate my sine and my cos, then there must be a triangle that I could draw in that situation. Lastly, you calculate the tan of 270, and all of a sudden you get this weird thing on your calculator that says error, which we know means undefined. There's something wrong with that calculation. So we want to kind of come back to this problem in a little bit, but we're going to address it as part of a larger issue. We can calculate the exact value of trig ratios when our terminal arm lies on an axis, even if we can't construct a triangle. So we're going to step back for a little bit, and we're going to work on all 4 parts of our axes moving forward. So what you see on the screen right now is just a big set of axes in the middle. And what I want to do is I just want to kind of work and deal with what should be kind of the easier situation for us. It's going to feel really weird. However, I want us to imagine that when we went through to rotate a certain angle, we were going to rotate no distance. In fact, we weren't going to rotate at all. And so therefore, our rotation was really 0 degrees. Now, when we take a look at that triangle is going to be difficult to create because I only see one terminal arm. I don't even see my initial arm. In fact, I don't even see my x-axis. So what I'd like everyone to do is we're going to kind of create something a little weird. We're going to create, in essence, what is a 2-sided triangle. What I would like everyone to do is to just imagine that your terminal arm was actually lying in the blue position. Now, we know that the terminal arm lies in the red position for an angle measurement of 0. But I want everybody to imagine that it lies in the blue position, because if it did, then we could drop in a height and we would now have our triangle. Okay, here's where we're going to do some stuff that's a little different, and I want you to hang with me for a second. Let's look at the triangle that's formed between the red, blue, and green lines. And on that, we don't have any side lengths labeled. And we know that to come up with the value of our ratios, we're going to need to label some side lengths. So the first question that I want you to think of is, if I was only supposed to rotate 0 degrees, which one of those side lengths doesn't really exist? Again, if I was to rotate 0 degrees, which one of those side lengths really doesn't exist? And I'm hoping that we can all point to the green side length. That if I was to rotate 0, then my blue arm should be lying directly on top of my red arm because it's the same arm. And so I wouldn't have any height over there in the green line. And so if I don't have any height over there, then what is the height? And hopefully we can come to the length of that green line should really be 0. It doesn't exist. Okay, well, we've got one side length labeled. Now I need to label the lengths of the other 2 sides. And here's where I would argue to you, you can label them anything you like, as long as one thing is clear. That whatever you label the length of the red side, the blue side must be the same. They are the same terminal arm. Remember, we were just imagining that the blue line existed where it did. If we rotated 0 degrees, the blue line lies directly on top of the red line. And so if they have to be the same angle measurement, length, then I'm just going to pick the easiest number to work with. I'm going to label them both as a length of 1. Now, you can do a quick little calculation, and you can confirm that my 3 side lengths, 1, 0, and 1, all fit within Pythagorean theorem. It just looks a little weird because I've actually created a triangle that could never exist. We often refer to this as an imaginary triangle because I could not create a triangle that has one side length being 0. So in essence, we built a 2-sided triangle. But now that I have all 3 of those sides, I can come up with all 3 of my trig ratios. I could calculate what the sine of 0 degrees was, because now I have opposite over hypotenuse. And so it's 0 over 1, which is 0. Confirm it on your calculator. I would have had a bunch of people that would have made the assumption that the value of sine of 0 was 0, Because if we start with 0 degrees, then we probably finish with 0 as a ratio. The one that may have surprised you, though, was to calculate the cos of 0. When we calculate the cos of 0, that is now adjacent over hypotenuse, which is 1 over 1, which equals 1. Confirm that ratio on your calculator. That one might have surprised us. The fact that we got a value of 1 for cos when we had a 0 degree angle. Lastly, calculate the tan of 0, and that would be opposite over adjacent, and that gives us 0 as well. Now, we just went through and we came up with the value of all 3 trig ratios, even when we didn't even have an angle. I want to clarify, we had an angle, but it was an angle measurement of 0. The other important thing, we actually found another angle's trig ratios as well, because we know that 0 would be the same thing as a full rotation, and so that would also be for an angle of 360. Confirm that on your calculator as well. And so what I want to do then is I want to move on and start rotating around our axes. So let's do the same thing. We are now going to rotate to where our terminal arm lies directly on top of our positive y-axis. So we now have rotated 90 degrees. Okay. It's really hard to create a triangle when your terminal arm is vertical. So, how can we imagine creating that triangle? What we can do is we can tip our terminal arm and imagine that it rotated a little bit past where it actually lies. And we know again that the blue terminal arm is the exact same thing as the red terminal arm. We're just imagining it lying in that position. Okay, now I can draw my triangle. Be very, very careful. There is going to be a big tendency to want to create your triangle here, and we have to stop ourselves. How do you always create your triangle? You drop your height to the x-axis. There is our triangle formed. And notice this time it doesn't even really use the red terminal arm. So I need to label the sides of that triangle. And the question we have to ask ourselves comes right back again. That on that triangle I just created, which side really doesn't exist? I have this opposite side over here. I have this adjacent side over here. And I have my hypotenuse. Well, clearly the hypotenuse exists because that is the terminal arm. So which one of those sides, opposite and adjacent, really doesn't exist if my terminal arm were to lie in the red position? Well, hopefully we can see that if my terminal arm was completely vertical, then I would have no adjacent side. And if I have no adjacent side, then I can plug in the value of 0 for that adjacent side. Well, if that side's 0, then why don't I work with the easiest numbers I can for the others? If my terminal arm is really vertical, then my vertical length is 1, and my terminal arm is 1. And again, if we do a little calculation, we can see that those all fit within Pythagorean. And now that we have those 3 sides of the triangle, we can determine our ratios. So I know that my sine of 90 degrees would be my opposite over hypotenuse. I know that my cos of 90 degrees would be adjacent over hypotenuse. And we might see something very interesting here on my tan of 90 degrees. My tan is going to be opposite over adjacent. And if I were to calculate 1 divided by 0, we see that we are going to get an undefined value because we can't divide by 0. That might give some people a little bit of a help to be able to work their way through and maybe see why something popped up a little bit earlier today as well. Okay, what I want to do then is I want to rotate a little bit quicker through the next 2 axes. So I'm going to pick up the pace considerably as we rotate through. So now my terminal arm rotates to an angle measurement of 180 degrees. If it's there, I can imagine my terminal arm rotating a little bit past where it actually lies. That enables me to drop in my height. Which side on that triangle really doesn't exist? This side, because my terminal arm is exactly horizontal, which means there is no height. And if there is no height, then that length is 0, which means my other 2 are my 1s. You may have caught something, and if you did, outstanding. I haven't put any directional signs on here. My 0 can't be negative because there's no such thing as a negative 0. However, I went to the left, and therefore my adjacent side is actually negative 1. For me to calculate my ratios, my sine 180 then is opposite over hypotenuse. My cos 180 is now adjacent over hypotenuse. And my tan 180 is opposite over adjacent. And we come up with those 3 ratios. Again, use your calculator to confirm. Now we're going to rotate all the way down to 270, which was the problem that we ran into earlier. Well, if I rotate 270, then what I can do is I can rotate a little bit past. That allows me to drop in my height. And again, I ask myself, which one of those sides doesn't exist if my terminal arm is really vertical? Well, if my terminal arm is really vertical, then my adjacent side, my horizontal side, must be 0. That means that my other 2 sides are both the same, so they are 1. But I have that directional component on my opposite side being negative 1 because I am going down. And so if I were to calculate then the sine of 270, that got really sloppy, is going to be opposite over hypotenuse. The cos of 270 is going to be adjacent over hypotenuse. And my tan of 270 is going to be opposite over adjacent. And that is why we found earlier that my tan ratio at 270 was undefined. So, on a big picture moment, what we've really added in today is we have the ability to find an exact trig ratio for any special angle on any rotation angle now. But we've also added in 4 more angle measurements, 4 more positions that your terminal arm could lie in, where you could also come up with the exact value. All of our rotations on an axis. So, your job today then, jump in and get some practice and make sure that we're comfortable coming up with all those values. Good luck.